This is a light bulb, which we can assume to be a purely resistive load. When we apply direct current to this light bulb, it turns on. We can depict the voltage and current across the light bulb over time in a graph like this. Since the voltage and current are constant, we can calculate the power used by the light bulb by simply multiplying the voltage and current. It's a straightforward calculation. If we neglect the wire resistance, we can confidently state that all the power supplied by the power source is consumed by the light bulb. Now let's consider another circuit containing the same light bulb, but powered using an alternating current power source. As we know, the current and voltage both change sinusoidally with time. Let's focus on one cycle. If both voltage and current change constantly, how can we rate this power source? In alternating current systems, we calculate the root mean square voltage and current values. The RMS values can be calculated by dividing the peak value by the square root of 2. We won't delve deeply into RMS values in this video. For a better understanding of RMS voltage and current, you can watch our previous video. I'll provide the link in the description. We typically calculate the power of an AC circuit by multiplying the RMS values of voltage and current. Alternatively, we can multiply each instantaneous voltage and current to graph the instantaneous power of the circuit. The power curve will look like this. It's important to note that negative voltage and negative current will result in a positive power. Therefore, the power is always positive. The area under the power curve represents the transferred energy. If we calculate the average power of this graph, it will be equal to the power calculated using RMS values. Still, we can say that all the power supplied by the power source is consumed by the light bulb. Right now, we have basic understanding about how we calculate the power of AC and DC circuits. Things start to behave differently when a reactive component is connected to the circuit. It's important to note that reactance can only be observed in AC-powered circuits. For a more in-depth understanding of reactance and resistance, check out our dedicated video. I'll provide the link in the description. Let's introduce an inductive reactance to this circuit by connecting an inductor in series with the light bulb. Now, what will happen? We know that the inductor does not like to change the current across it. So instead of changing with the voltage, the current will change after the voltage. In this scenario, we can say the voltage leads the current, or the current lags the voltage. If you are not familiar with inductance, I highly recommend watching our inductance video. Due to this lag, there are instances where voltage is positive, but current is negative, and vice versa. Let's focus on one cycle. What has happened to the power now? We can calculate the instantaneous power over one cycle as before. We can observe negative power regions where the current is negative while the voltage is positive and vice versa. This negative power doesn't imply that the load is generating energy. Instead, it simply means that during those brief moments, the power flow reverses direction, with the stored energy in the magnetic field of the inductor temporarily returning to the source. Let's attempt to explain this more clearly. Here is the voltage and current graph of our circuit. Now, let's draw the power graph again. As mentioned earlier, there are negative power regions and positive power regions. At the beginning, power is positive, indicating that the source delivers energy to the circuit. Part of this energy is used to create the magnetic field around the inductor and the remaining energy is used by the light bulb. The negative part represents the energy stored in the magnetic field of the inductor. Now, the magnetic field is discharging, and the energy is flowing back to the source. However, this energy does not go in a useful way. It only exchanges back and forth between the source and the inductor. During this period, the light bulb does not receive energy. This process repeats. Now let's compare the two circuits. The resistance of the light bulb is the same for both circuits. The RMS voltage of the power source is equal in both. Let's assume the RMS current for both circuits is equal. Voltage and current for both circuits can be plotted like this. Now let's draw the power graph. In circuit A, the power is always positive, indicating that all the energy supplied by the power source is consumed by the light bulb. However, in circuit B, there are negative power regions. Only the positive regions represent the energy transferred from the power source to the light bulb. Let's focus solely on the energy transferred from the source to the load. In circuit B, it's evident that due to the effect of the inductor, the amount of power received by the light bulb has decreased. However, the power source still supplies the same RMS voltage and current. Let's calculate the average power consumed by the load in these circuits. As we discussed earlier, for circuit A, the average power is equal to its RMS voltage multiplied by RMS current. However, it's clear that the average power of circuit B is less than its RMS voltage multiplied by RMS current. Now, let's focus on circuit B. The load requires this much power to operate properly, and the source is supposed to supply that amount. However, due to the inductive reactance of the inductor, the load only receives a reduced amount of power. In order to receive the required power at the light bulb as before, the load has to supply more power than earlier. Therefore, the load has to increase the current. Let's compare this with circuit A. Even though the load receives the same power in both circuits, in circuit B, the load has to supply more. So, it seems some amount of energy goes to waste in circuit B. Let's summarize. In alternating current circuits, if there is a net reactance, the circuit's current will lead or lag the voltage. When we draw the power graph based on this VI graph, we observe both negative and positive power flows. This occurs because the power is divided. Part of it energizes the load, while some power is stored by the reactive components of the circuit. This stored power in the reactive components flows back to the power source with each cycle. Therefore, it's evident that reactive components do not consume power. Instead, they store and release power back. We will only focus on the power coming from the power source to the circuit, disregarding the negative power flow. Now, it appears that the energy from the power source is consumed by both the load and the inductor. This can be illustrated in the power graph like this. By averaging these values, we can illustrate the energy distribution. The energy transferred to the reactive components doesn't perform useful work, so we refer to this power as reactive power. We can calculate the reactive power of a circuit if we know the reactance, voltage, or current. Only the energy transferred to the resistive load performs useful work, known as real power or active power. We can calculate the active power of a circuit if we know the resistance, voltage, or current. The amount of power expected based solely on the RMS voltage and current of the power source is called apparent power. It can be calculated by knowing two of voltage, current, and impedance. However, apparent power might be higher than the real power dissipation because of the lagging or leading between voltage and current, which creates reactive power contributing to apparent power. This is why it's called apparent. Normally, we measure power using watts. However, here we have mentioned three types of power. If we measure all three using watts, it will be confusing. Therefore, we only measure the active or real power using watts because it is the power actually doing the work. As discussed before, reactive power does not actually do any work. It oscillates back and forth between the power source and reactive components. However, it causes an increase in current in the circuit, so it is important to measure this power. Reactive power is measured using volt-amperes reactive or VAR. Apparent power represents the total power seemingly available in the circuit. Since apparent power includes both real and reactive power, measuring it in watts wouldn't provide a complete picture. It would only represent the real power component, omitting the important information about the reactive power present. Therefore, it is measured using volt-amperes, VA. These three types of power, true, reactive, and apparent, are interrelated and can be represented graphically by what we call the power triangle. The power triangle is a right-angled triangle. The horizontal or adjacent side represents the circuit's real power P, the vertical or opposite side represents the circuit's reactive power Q, and the hypotenuse represents the resulting apparent power S. The angle between the real power and apparent power signifies the impedance phase angle. By applying trigonometric principles, we can calculate the length of any side given the lengths of the other two sides, or the length of one side and an angle. When powering up any type of load, it's crucial to assess how much of the supplied power is effectively utilized to perform work in a circuit. Engineers utilize the ratio of actual, real power to the apparent power, termed as the power factor of a circuit. Power factor serves as an expression of energy efficiency, ranging from 0 to 1, typically represented as a percentage. The lower the power factor, the less efficient the power usage. If the power factor is equal to 1, that means active power and apparent power is equal, hence there is no reactive power. All the power supplied by the power source is going to the load to do work. If the power factor is less than 1, it indicates that the apparent power is larger than the active power. This implies that some of the power is wasted as reactive power. A lower power factor indicates that more power is wasted as reactive power, rendering such circuits highly ineffective. They draw an unnecessary amount of current. This reactive power necessitates generators, transmission lines, and transformers to be oversized to handle the additional current, despite not performing any productive work. This oversized infrastructure increases capital and maintenance costs for the power company. Additionally, reactive power causes voltage fluctuations and energy losses in the transmission lines, further reducing efficiency. By charging a penalty for low power factor, power companies encourage customers to improve their power factor and reduce their reliance on reactive power. What causes the low power factor? Most of the time, a low power factor is caused by inductive loads connected to the power lines. Inductive loads like motors, transformers, solenoid valves, and relays draw reactive power, which creates a magnetic field but does not contribute to actual work. How to improve the power factor? As mentioned earlier, inductive loads, such as motors, cause current lag. However, capacitors behave oppositely to inductors. They lead the current. To counteract the effect of inductors, We can install capacitors that lead the reactive power, thus offsetting the lagging reactive power from inductive loads. This effectively cancels out the lagging power and improves the overall power factor. Capacitor banks are relatively inexpensive and require minimal maintenance. I believe you now have a clearer understanding of what occurs when there is reactance in a circuit. Let's proceed with some power factor calculations to reinforce these concepts. Imagine we have connected an induction motor to our 120-volt 60 Hz main power supply. If we only consider the resistance, we can draw the circuit like this. The resistance of the motor is 60 ohms. From there, we can simply calculate the RMS current through the circuit, which will be 2 amperes. Now let's calculate the power supplied by the power source. This represents the active power of the circuit. Since we're neglecting the reactance, the apparent power is equal to the active or real power. Therefore, the power factor is equal to 1, indicating that all the power supplied by the power source is effectively utilized to do the work. Things may seem straightforward, but unfortunately, this method is incorrect. Indeed, neglecting inductance for inductive loads like motors is not accurate. Let's consider both resistance and inductance now. The inductance of this motor is 160 millihenry. Now, the calculations are more complex than before. We need to calculate the power factor, which requires knowing both the apparent power and active power. The apparent power can be calculated using the impedance of the circuit and current, while the active power can be calculated using resistance and current. Resistance is given. However, we don't know the current and impedance of the circuit. To calculate the current, we also need the impedance and voltage. Voltage is given. To calculate the impedance, we need to know both the resistance and reactance of this circuit. We're given the resistance, but to calculate the reactance, we require both the inductive and capacitive reactance. Since there is no capacitance in this circuit, the capacitive reactance is 0. Therefore, we only need to calculate the inductive reactance. To do this, we require the inductance and frequency, both of which are known. This is where we should start our calculations. As you can see, it's a more complex process. Right. Let's do the math. First, we need to calculate the inductive reactance, given that the resistance is provided and the capacitive reactance is 0. With the inductive reactance determined, we can then calculate the impedance of this circuit. With the voltage provided, we can calculate the current. After obtaining the current, we can calculate the apparent power using the impedance and current. Then, the active or real power can be determined using the current and resistance. Now, we move to the final step, calculating the power factor. It seems the power factor of this system is 0.705, which is less than 1. That means only 70.5% of the power is utilized for work, while the rest is lost within the circuit. This indicates inefficiency. To improve this, we can connect a capacitor to increase the power factor. Let's see how it's done. The poor power factor is primarily due to the inductive reactance. To counteract this, we need to add a capacitor in parallel to our example circuit. Let's determine the value of the capacitor we need to connect. The capacitor is meant to counteract the inductive reactive power of the circuit. Therefore, our first step is to determine the inductive reactive power of this circuit, which we aim to minimize. Now, we have to connect a parallel capacitor that generates an equal and opposite capacitive reactive power to cancel out the total reactive power. So the capacitive reactive power should also be 119.92 VAR. Now, we need to calculate the correct capacitive reactance to produce an equivalent amount of capacitive reactive power in this circuit. It's important to note that adding a capacitor will alter the current. Therefore, we can't employ the same current value to calculate the capacitive reactive power. As this capacitor will be directly connected in parallel with the source, we'll utilize the power formula which begins with voltage and reactance. we have determined the reactance of the capacitor. Now, let's find the capacitance required to achieve this reactance in the circuit. Eureka! We have calculated the capacitance. To correct the power factor, we need to install a 22.09 microfarads capacitor bank in parallel with this circuit. That's all for today. If you think my contents are valuable to the world, you are welcome to join my Patreon community. Like and subscribe to Professor Mad for more interesting videos.